Let's look at another interesting problem. We have to find two straight lines, CM and D, which are medial straight lines, commensurable in square only, such that their product is rational. And CM square is greater than D square by LM square, where LM is commensurable with CM. Okay, let's proceed. We start off by taking a straight line A, and then we take two square numbers, say 16 and 4, such that P square minus Q square is not a square number and P square is greater than Q square. We arrive at another straight line B such that A and B are commensurable in square only. We have already seen how to do this. So we have arrived at B. So we have taken two straight lines A and B such that they are commensurable in square only. Let's take a straight line C such that it is the mean proportional between A and B. So here this would be like CM is equal to square root of A times B. That means CM square is equal to A times B. Or in proportionality form, we can write it as A is to CM is equal to CM is to B. That's what mean proportional means. Okay, now we find another straight line such that B is the mean proportional between D and CM. So here D is equal to B square by CM. That means B square is equal to D times CM. In proportionality form, it will be D is to B is equal to B is to CM. So CM is the mean proportional between A and B, and B is the mean proportional between C and D. What we have achieved is we have found two straight lines D and CM, which are also commensurable in square only, and their product is rational. So product means the rectangle contained by D and CM. So here EF is equal to CM and EH is equal to D. Now, it's fine for me to say this, but how do we actually know that whatever I have said is correct? Or in other words, CM and D are the required numbers or required magnitudes. Let's figure out what CM actually is. So CM is equal to square root of A times B. Now we do the substitutions. So square root of A times square root of 1 minus Q square by P square. Now here we have A square. So that can be taken out of the square root so that we have A times square root of 1 minus Q square by P square. In other words, this is nothing but A times 1 minus Q square by P square to the power of 1 by 4. Fourth root. So that is what CM is. Now let's look at what D is. D is equal to B square by CM. Let's do the substitution. B is A times square root of 1 minus Q square by P square. So when we square it, what we get? We get A square and the root disappears because of the squaring. So we end up with A square times 1 minus Q square by P square divided by CM, that is A times 1 minus Q square by P square to the power of 1 by 4 or fourth root, which can be simplified to here the power is 1, here the power is 1 by 4. So 1 minus 1 by 4 is 3 by 4. One of the A's will get cancelled out here. So A times 1 minus Q square by P square to the power of 1 by 3 by 4. Okay. So we have found CM, we have found D. And here both CM and D are medial straight lines. And what we are claiming is that the product of CM and D is a rational area. So let's see. Now D times CM is equal to D is B square by CM times CM. So CM cancels. So the area D times CM is equal to B square, which is equal to A square times 1 minus Q square by P square, because the square root cancels out with the square. And here, if you notice, there are no roots. That means we can say that this is a rational magnitude. Now, if I had just shown you these values, CM is equal to this and D is equal to this and D times CM is equal to this. Yes, D times CM 27, we could have said it is a rational number. But in these two cases, we can't say that these are medial. It is only when we write it in this form, we know that these two are medial straight lines. Medial straight lines are nothing but where you have a fourth root. Now, that's not the end of it. We also have to figure out LM such that CM square is greater than D square by LM square, where LM is commensurable with CM. So this we have seen how to figure out LM square. We draw a semicircle on CM and we draw a line within this semicircle such that it is equal to D. So we draw a circle with center C and radius as D. Take the intersection and we join C and L. CL is equal to D. That means if we join LM, this is a right angle triangle because it's in a semicircle, and we can say that CM square is greater than CL square by LM square. So this part is taken care of. Now we have to show that LM is commensurable with CM. For that, we have to figure out what LM is. So LM using Pythagoras theorem is equal to square root of CM square minus CL square. Doing the substitutions, we get square root of CM square. And square on this would be 1 by 2. So let's keep this A inside, then it will be A square times 1 minus Q square by P square to the power of 1 by 2. Minus CL is equal to D. Now again square of D, because that is equal to CL. So A times 1 minus Q square by P square to the power of 3 by 4. So when we square this, we get A square times 1 minus Q square by P square 3 by 2. Now A square is common to both of them, so we have taken it out of the square root as A. How do we simplify this further? You will notice that this 1 minus Q square by P square to the power of 1 by 2 is common to both. So we take it out. So we have A times square root of 1 minus Q square by P square to the power of 1 by 2 times 1 minus 1 minus Q square by P square. Because here the power is 1, 1 plus 1 by 2 is 3 by 2. And now here 1 and minus 1 will cancel out. So we'll be left with A times square root of 1 minus Q square by P square to the power of 1 by 2 times Q square by P square, which is equal to the squares Q square by P square. If we take it out of the square root, the squares will disappear. So A times Q by P times 1 minus Q square by P square to the power of 1 by 4. So that means LM is a rational multiple of Cm. Because here also you have 1 minus q square by p square to the power of 1 by 4. Here also you have that. So it is a q by p multiple of Cm. That means they are commensurate. So we have shown, or rather, we have found two straight lines, Cm and D, such that Cm square is greater than D square by Lm square, where Lm is commensurable with Cm. Now, without using all these algebraic notations, Euclid did this in his book Elements, book 10, proposition 31. Interesting, right? That's it for now.